Bienvenue tout le monde à cette nouvelle saison des séminaires de mathématiques physiques au CRM. Welcome everyone to this mathematical physics seminar series. We're starting this semester on Zoom, but already next week we'll have a talk in hybrid mode with the speaker in person, and this will also be broadcast online. And we'll see how things go, but most of the talks are by Zoom. And also for the, if you have any people you wish to invite, please let me know. I'm in charge of monitoring the list. And in the chat, we added a new page with all the seminar speakers. They're not all there yet, but the first 3 are there yet. So keep a look on that. And without further ado, I'm going to introduce today's speaker. I'm going to launch the series. It's Rufus Boyack, who's a postdoctoral fellow in my group. Rufus started a year ago, more or less. And prior to coming to Montreal, Rufus was a postdoctoral fellow in Alberta, in a group of Joseph Macheco, working on quantum criticality, quantum phases of matter, superconductivity. And he did his PhD at the University of Chicago with Catherine Levin, studying a lot of things, including high temperature semiconductors and their response. So these are very enigmatic phases of matter. And so Rufus is an expert on studying strongly correlated quantum systems. And today he'll talk about one such class of systems, which are phase transitions into or out of spin liquids. And he'll discuss various critical properties of these systems. So Rufus, the floor is yours.
Thank you very much, William. And thank you everyone for attending today's talk. It's a pleasure to give the first talk for the seminar. So yes, today I'm going to tell you a story about the critical properties of quantum spin liquid phase transitions. This work has been done in collaboration with many people, and I would just like to take the opportunity now to thank them for all their valuable contributions to this body of work. And I would like to thank the following institutions for providing funding, which has made this work possible. So this is the outline of my talk. It's roughly divided into 4 different sections. I'll begin with an introduction to spin liquids and conventional magnetic phases of matter. Then I will discuss a duality conjecture between the phase transition in 2 different spin liquids and the phase transition in 2 different conventional magnetic phases. Then I will discuss the critical properties of a U1 spin liquid and the Néel phase and the U1 spin liquid and the VBS phase. And then I will discuss monopole scaling dimensions for the transition between a U1 spin liquid and 2 different types of topological spin liquids. So first, let me discuss what spin liquids are and some familiar magnetic phases of matter. So as we know, in an ordinary liquid, the molecules form a dense, highly correlated state, and they have no static order. So for example, in water, you find that the water molecules are continually fluctuating, undergoing Brownian motion. And when we consider the spins on a triangular lattice, we also observe this fluctuation phenomenon due to geometric frustration. So frustration occurs, for example, when we have this triangular lattice and in the presence of antiferromagnetic interactions, which favor all the spins being aligned antiparallel, you can see that there's some frustration at this 3rd lattice point. We can't have 3 spins all being antiparallel to one another. So what occurs is, in fact, you have the spin at this lattice site here will fluctuate between spin up and spin down. So what a quantum spin liquid is a system that has no magnetic order. It's a paramagnet, yet it has spin fluctuations due to this geometric frustration. So it's a quantum superposition of many fluctuating different spins. And due to this phenomenon, there's a lot of exciting and exotic particles that can emerge in this system. So this leads to fractionalization and the presence of artificial gauge fields. And we can understand that as follows. So at this third lattice site, you can have a spin singlet, where you have spin up and spin down superposition. But we can imagine that these two spins can be separated and interact via an artificial gauge field. So here, these isolated spins are called spin-on degrees of freedom, and this artificial gauge field mediates their interaction. So I'll come back to this in a moment, but the thing to keep in mind is that a spin liquid is a paramagnet, so it has no magnetic order, but it has spin fluctuations due to geometric frustration. So spin liquids, as I just said, are the highly entangled phases of matter, and this entanglement can persist even down to 0 temperature. So it's a quantum property. The particular spin liquid that I will be discussing today is known as the U1 quantum spin liquid, also the abelian spin liquid or Dirac spin liquid. These are all synonyms. And in this system, we have gapless Dirac fermions, which interact with a U1 gauge field. There are some materials in nature which are conjectured to be realizations of such a system. So one such material is Herbert-Smithite, given here. Here is a plot of the structure factor measured in neutron scattering for two different directions in the reciprocal lattice space. So what you have here is a plot of the energy versus the wave vector. And usually in neutron scattering experiments, what you find is that there'll be a resonance associated with the excitation of a magnon. But here you see that for a fixed wave vector, there's a broad range of, a continuum range of energy. So there's no resonances observed in this system. And therefore people believe that this is an example where these spin-on degrees of freedom are actually excited and not magnons. So this is believed to be an example where the ground state is a U1 spin liquid. Another example is this organic material here. The heat capacity per temperature was measured as a function of T squared. And spin liquids have a very large ground state degeneracy. They have a large density of states. And as we know from Fermi liquid theory, the low temperature specific heat is expected to be linear in temperature. And here you see that the heat capacity is going to a constant. Heat capacity per temperature is going to a constant, which is enigmatic of such a phase. There's no exponential suppression, which you would expect for a gap system. So this is indeed gapless and has a large density of states. And this upturn that they see at very large temperature is sort of it's an anomaly, which is, it's understood, but it's not a signature of the U1 spin liquid. So let me go into the mathematical details of what a spin liquid exactly is. We start off by considering an antiferromagnetic spin model, which is described by some Heisenberg Hamiltonian. So J here will be positive for antiferromagnetic interactions. The standard procedure is to do what's known as a slave fermion description. So here we write a single spin degree of freedom in terms of two fermion operators, these C dagger and C. So this is what's sort of known as fractionalization. We've taken a single spin degree of freedom and separated it into its individual fermionic constituents, so to speak. Now, when we make this ansatz in the Hamiltonian, we'll get a Hamiltonian that now has a 4 Fermi interaction for the C and C dagger operators. And we can perform mean field theory on that, which leads to a quadratic Hamiltonian for the C operators. So chi here corresponds to the expectation value of a fermion bilinear. We can then consider phase fluctuations in the mean field ansatz, and that leads to the presence of an artificial gauge field. So you can convert this purely spin Hamiltonian into what's known as three-dimensional quantum electrodynamics. So you have massless fermions, and the phase fluctuations and the expectation value of the mean field ansatz corresponds to the U1 gauge degree of freedom. So this is what we mean by a U1 quantum spin liquid. Its phase, it has massless Dirac fermions. and they are interacting with a U1 gauge field. So it's known from high energy that the three-dimensional quantum electrodynamics is a conformal field theory for sufficiently large number of fermion flavors. And what I will be discussing in this talk is how we can have phase transitions from this U1 quantum spin liquid into phases which have magnetic ordering. So we go from a phase that has no magnetic ordering to magnetic ordering.
Sorry, I'm a little bit confused. Your first Hamiltonian is just Pauli matrices, and then you have Dirac matrices. So is this relativistic?
These in 3 dimensions, these gamma matrices will be Pauli matrices. So gamma mu will be.
Oh, the mu's don't sum over 4; they sum over 3.
Yes, this is 3 dimensions. So this will be gamma mu is sigma 3, sigma 1, sigma 2.
Okay.
So yes, so sorry for the notation, but the gamma matrices are Pauli matrices.
So really, it's just a magnetic field. It's not an electric field. The A mu is 3-component vector potential, right?
Yes, but
no, I mean, there's sorry to interrupt. There's electric components as well, right? I mean, there's 1B
But
field.
there's no time component. There's no density. Right.
So F01 is E and F12 is the magnetic field. So for example, okay, that's a good point. When we do this, when we rewrite a spin in terms of 2 fermion operators, that actually enlarges the Hilbert space. And in order to make the Hilbert space have the same degree of freedoms, we introduce a constraint, which is it's called A0, and that constraint acts as the time component of the gauge field. Here we have this phase parameter, which acts as the vector components of the gauge field. So there is an A0, an A1, and an A2. They come from slightly different origins, but there is an electric field and a magnetic field. So A0 emerges from the constraint on the Hilbert space, and A1 and A2 emerge from phase fluctuations in your mean field ansatz. So in condensed matter physics, one of the standard approaches for describing different phase transitions is the Landau-Ginsburg-Wilson theory. And in this framework, we have an order parameter which characterizes different broken symmetries. So for example, if we consider a ferromagnet, the magnetization plays the role of an order parameter. And in the paramagnetic phase, magnetization is 0. And in the ordered phase, the magnetization is non-zero. However, it's interesting to ask what happens in the Landau-Ginsburg-Wilson theory when we have a transition between 2 phases that break different symmetries. And in general, since the order parameter has to describe a broken symmetry, it's not possible to go between 2 different phases that break different symmetries continuously, that is. You would have to have some. Oh, sorry. I think I muted myself.
You're back.
Okay. Did you hear me talking on this slide?
Yes, we did. It was just a very, like 5 seconds roughly at this slide.
Okay. Well, I'm just to recapitulate, I was just saying that in condensed matter physics, we use the Landau theory to describe phase transitions. But one of the deficiencies of this framework is that it doesn't allow us to go between different phases that break different symmetries. So I'm going to be talking about that quite a bit. So we need to understand how we can formulate that theoretically. So I'm going to discuss that in the context of 2 familiar magnetic phases, the Néel phase and the valence-bond-solid phase. So we want to consider 2-dimensional antiferromagnets on a square lattice. These have the following Hamiltonian. As I said, J is positive for antiferromagnetic interactions. In the Néel phase, you find that on each lattice site, the spin will be either spin up or spin down. So we have a long range antiferromagnetically ordered state, and this phase spontaneously breaks the spin rotation symmetry. So if we were to use a Landau framework for this theory, we would use an O3 vector model plus some other additional features, which I won't go into. A paramagnetic phase of interest is known as the valence-bond-solid phase, and in this phase you find that the spins on each lattice site pair in these spin singlets, and they resonate between spin up and spin down. And there are 4 different ways you can have this columnar VBS order. So if you just take this picture and rotate it 90 degrees about a specific lattice site, you'll get VBS order in the X, or two types of VBS order in the X and in the Y direction. And this type of theory is described by a Z4 clock model. Although this is a paramagnetic phase, it's not quite the same as the spin liquid I was mentioning earlier, because it breaks translation symmetry. And what we would like to describe is how we can formulate a theory that allows us to describe the transition between a Néel phase and a valence-bond-solid phase. And this leads to the notion of a deconfined critical point, which asserts that at the transition point between these 2 different phases, there are emergent excitations which manifest at the transition point itself, but they may not be present in these specific confined phases themselves. So this will become more clear when I discuss this particular model. This is known as the Cp1 model, or non-compact Cp1 model, to be more specific. And it describes the Néel VBS transition. So here you have these complex numbers. There's 2 of them, Z1 and Z2. They satisfy this constraint. And this theory has been shown to be able to describe the transition between the Néel phase and the VBS phase. So in the Néel phase, one uses this order parameter, which is the SO3 symmetry. You construct a order parameter from Z dagger and Z. Sigma is the Pauli matrices. The VBS order parameter is a little bit more subtle, but you can formulate a VBS order parameter from these spin degrees of freedom. So these Z parameters are known as spin-ons because you sort of fractionalize the order parameter into these 2 spin degrees of freedom. Now the Néel and VBS order parameters, they have a U1 SU2 symmetry. So Néel has rotation symmetry and the VBS has a U1 symmetry. And you can form this quintet order parameter from these 2 specific order parameters. So now you have an order parameter with 5 components. And very interestingly, some quantum Monte Carlo calculations have found that at the transition point itself, this U1 SU2 symmetry is enhanced to an SO5 symmetry. And this has been a topic of a lot of interest in condensed matter physics. So I'm going to now show how this this phase transition between these 2 magnetic phases is related to another phase transition in the U1 spin liquid I mentioned earlier. So this is the second part of my talk where I'll be discussing a duality conjecture between the Néel VBS phase transition and a phase transition in a particular spin liquid. So the particular theory that I'm going to consider for the spin liquid transition is known as QED-GN. This is 3-dimensional quantum electrodynamics, Gross Neveu Yukawa theory. So it has all the features that I mentioned in the case of 3-dimensional quantum electrodynamics. It has massless fermions interacting with a U1 gauge field. And now what we incorporate for the Gross Neveu Yukawa interaction is we add a scalar field, a real scalar field, which has a Yukawa interaction with the fermions. There's of course the Maxwell kinetic term, and there are scalar interactions. So this scalar field tunes a transition between 2 different spin liquids. So in the case where the scalar field has 0 vacuum expectation value, we have the U1 spin liquid, which I mentioned earlier. And in the case where the scalar field acquires a vacuum expectation value, these fermions acquire a mass. So we have time reversal symmetry is spontaneously broken, and we have what's known as a chiral spin liquid. So this scalar field tunes a transition between a direct spin liquid and a chiral spin liquid.
So the phi is a Higgs field.
Say that once more.
The phi is a U1 analog, or I don't know, a one-dimensional analog of a Higgs field, right?
Yes, you can think of that. It's just that, yes, it's spontaneously breaking the U1 symmetry. It's not quite the same in that we're not going to be talking about giving the gauge field a mass, but it plays a similar role. I will discuss a theory where the scalar field is a Higgs field, but think of it as this is like spontaneously breaking chiral symmetry, as you would see in say the Nambu-Jones-Lacina model.
But this is not like the energy gap in superconductivity.
Right. So here phi is coupled to psi bar psi. If phi were to be coupled to psi psi or psi bar, then that would be the analog of superconductivity. But this is coupled to an object which is U1, psi bar psi is U1 invariant. So this is not the analog of superconductivity yet. I will discuss a model later on which has a remnant of the abelian Higgs model, which you're referring to.
But Rufus, you said the U1 gauge symmetry is broken. I mean, but it's not, right?
No, I didn't. I said that.
Okay, maybe I misunderstood.
If here psi bar psi is U1 invariant, if we were to have phi coupled to a psi psi or a psi bar interaction, the U1 symmetry would be broken. So what I'm saying is that phi is breaking time reversal symmetry, not U1 symmetry.
Yeah, no, of course. It's a real field. It's not charged in order U1, so it's not a Higgs field.
Exactly. It's not a Higgs field. I will discuss later in the talk such a field, but this is not a Higgs field. That's right. So this theory has a global SUN flavor symmetry where this big N is the number of two-component massless Dirac fermions. And it's very important that we work with a theory in 3 dimensions. One can formulate this theory in 4 dimensions and perform dimensional reduction to 3 dimensions. But if you do that, you actually find that you don't have the full SU big N symmetry, which is SU2NF, where NF is the number of 4-component spinors. You actually have now a SUNF cross SUNF symmetry. So what this means is that there really are 2 QED-GN theories, and this will be important when I come to discussing this particular duality. For the moment, just keep it in mind. So this duality conjecture, which was formulated by Chong Wang and collaborators recently, is formulated as follows. The Cp1 model, as I mentioned earlier, has an SU2 cross U1 symmetry, and it's been observed numerically that it's enhanced to SO5 at the transition point. This chiralizing QED-GN theory that I just mentioned, which describes the transition between a U1 spin liquid and a chiral spin liquid, has an SU2NF cross U1 symmetry. So if we have one 4-component direct fermion, it has the same SU2 cross U1 symmetry as the Cp1 model. And it also has an emergent SO5 symmetry. So the conjecture by Chong Wang and collaborators is that the critical point in these 2 theories are dual to one another. And I just want to emphasize that this is quite an amazing conjecture, because you have a transition between 2 ordered magnetic phases. So the critical point between an AL phase, which breaks spin rotation symmetry, and the VBS phase, which breaks translation symmetry, is conjectured to be dual to the critical point that is observed between a transition from a U1 spin liquid, which is a paramagnetic phase, and a Carro spin liquid. So it's it's an amazing conjecture, and I'm going to test some of the consequences of this conjecture.
Can you
I have a question.
specify a little bit what you mean by dual here?
It just means that, well, they have the same. Well, I'm going to get to that on the next slide. Hopefully that will clarify. So we have a theory which has a theory which describes a transition between two different phases, and another theory which describes a transition between two distinct spin liquid phases. So at the moment, the Néel to VBS transition is, as I said, seemingly quite unrelated to this. This is a transition between two magnetic phases. This is a transition between two spin liquids. They need not be related a priori, but they both have the same emergent SO5 symmetry. And when we say that they are dual, we mean that the order parameter in each of these theories are equivalent to one another. So we have a 5-component order parameter for the Néel VBS transition. We can formulate a 5-component order parameter for the QED-GN transition. The statement that these two transitions are dual to one another is the statement that the respective order parameters must be equal. So in particular, what that means is, in the case of the chiralizing QED-GN theory, as I mentioned, the scalar field is the parameter that tunes the transition. So that's one component of this big 5-component order parameter. And the statement that these transitions are dual to one another means that the VBS order parameter and the Néel order parameter should have the same scaling dimension as the order parameter for the QED-GN theory. So the parameter eta here is an anomalous dimension, so that just characterizes the scaling of your correlation function and its difference from the naive scaling dimension. So this duality conjecture is, the question mark here is the statement that the scaling dimensions, anomalous dimensions, excuse me, for the Néel VBS parameters should be equal to the anomalous dimension for the QED-GN theory. This is another duality. I won't go into what it actually means, but I'll just say that the duality just means that the scaling dimensions of the order parameters must be equal.
So it doesn't mean that all correlators could be calculated one way or the other way.
Yes,
I think so.
it
I think
does.
the strong version of duality maps all operators, their partner operators between these two conformal field theories.
Maybe not the operators, but the correlators.
No, the operators, I mean, well, and everything that follows from that, because, but I think that the point is that it's in the infrared, these two descriptions correspond to the same infrared physics. So the same conformal field theory with the same operator content and the same anomalous dimensions or scaling dimensions, the same OP coefficients and everything that you want. But it's a conjecture at this point, and probably not exactly realized, but maybe approximately. But the conjecture, the strong version, is that the theories are equal in the infrared, the two CFTs, because they are CFTs, conformal field theories.
He didn't mention that. Nobody mentioned that.
Yeah, Rufus, you didn't mention, but a lot of the things that you're discussing are conformal field theories in 3 space-time dimensions. So it's
Is there some way to see the conformal invariance?
Well, it's QED-3, and we know from high energy theory that QED-3 is a conformal field theory for sufficiently large n. The large n calculation was done in the 1980s.
So there's no dimensional coupling constant, I guess.
Well, 8 pi squared e, forget exactly the coefficient, but usually 8 pi e squared or some variant of that plays the role of the coupling constant.
But is that dimensional?
E squared has units of 1 and 3 dimensions, but here we're not doing any running of the coupling or anything. So there's no, what value E squared takes is not pertinent for this discussion, but
well,
E
pure
squared is
electrodynamics is conformally invariant, but you've got these extra fields, the phi's and the psi.
yes, that is correct.
No, in 3 dimensions, pure electrodynamics is not conformally invariant. It's super normalizable.
Pure electromagnetic?
Yeah, because the gauge coupling in 3D has mass dimension 1.
Ah.
But then if you start adding matter and then you take the number of fermions to infinity, it flows to a conformal fixed point. So it's in the infrared is well defined.
So this is conformally invariant in the n equals infinity limit.
No, I mean,
No?
at large enough n, I mean, you have enough control to argue that the CFT fixed point exists. So when n is infinite, you can solve the system exactly, and then yes, it's true, but it holds beyond n being infinite. The question here is like when n becomes finite and small, whether these are actually CFTs that are unitary, and that's a much more difficult question. But there's enough data now and analysis that beyond a certain finite n, let's say 10, that this describes conformal fixed point, both the bosonic and the fermionic version extend them to having a number of flavor fields. So it's not only a Gaussian statement when n is infinite, which would not be very interesting.
So one of the important facts about this duality is that it holds in specific to 3 dimensions. So we can't use dimensional regularization because there's no d-dimensional representation of the Clifford algebra. So we have to work in 3 dimensions explicitly. And perturbative parameter we use is the number of fermions. So this is how we group the Feynman rules using the large N approach. So we construct a large N gauge propagator, which consists of summing all of the contributions that have the same powers of N. And similarly, we do the same for the gauge field. So all of these diagrams have the same power and the number of fermion flavors.
So maybe I've asked the wrong question. So it's not that the Lagrangian is conformally invariant for finite n. It's that somehow at the critical point, there's some sort of a conformal invariance in the parameters.
Yes. At the critical point is expected to be a conformal field theory. That's right. So at the critical point, we have the expectation value of the scalar field vanishes, and as was mentioned, QED-3 is known to be a conformal field theory for what the explicit value of n is not exactly known, but it's many different calculations have shown that it's smallish, but for sufficient n, well, let's just say if n is infinity, then yes, QED-3 is a conformal field theory. So this fixed point is a conformal field theory. So these are the bare Feynman rules that we have for this large N framework. We have a fermion propagator, gauge propagator, and a scalar propagator, and likewise we have these Yukawa interactions. I will just highlight one of the important features of this three-dimensional calculation. So in the presence of when we do this calculation in 3 dimensions, there are diagrams known as Haslem-Larkin that just comes from the superconductivity literature, but the nomenclature is not too important. But as you can see from these triangle vertices, that when we perform the trace of 3 gamma matrices, that's only non-zero at 3 dimensions. So these contributions are very important when we work in 3 dimensions. And just as an example, if we were to calculate the inverse correlation exponent, and if we were to ignore these contributions, we get this result on the second line. And if we incorporate these contributions in the inverse correlation exponent, we get this result on the third line. So you can see they have a very large large and important contribution. And for the duality, we need to incorporate these contributions. So these are the analytical results for the large N calculation. Since we want to extrapolate to n equals 2, we perform Padé and Padé-Borel resummation. And the result that we find for the anomalous dimension of the scalar field is either 0.17 or 0.30. And the numerical value for the anomalous dimension of the Néel or VBS order parameters have been calculated in quantum Monte Carlo, and those are either between 0.25 and 0.35. So while of course we've just done the large N calculation to 1 over n, we cannot prove it exactly, but the results are compatible with this duality. So this gives credence to this expected duality, which is, as I said earlier, quite surprising. So that's the first part of this talk I'm going to move on from. So I just wanted to say that yes, we observe this agreement with this duality, which conjectures that these operators, as William said, there's a strong version of this duality and a weak version. But here I'm just saying that the scaling dimensions of these operators should be equal. And here we find rough agreement with that. So now I'm going to discuss the critical properties of a different type of phase transition from a U1 spin liquid. So before I was discussing the transition from a U1 spin liquid to a chiral spin liquid, but now I will be discussing the transition from a U1 spin liquid to a magnetic phase. This was recently observed in some very exciting quantum Monte Carlo studies by Ziyang Ming's group. And what they performed is a sign problem-free quantum Monte Carlo study of a rotor model. So this is a realization of lattice quantum electrodynamics. So this is just a pictorial representation of what they were considering. So this blue dot means we have a fermion on the lattice site, so C or C dagger. This orange open circle corresponds to the gauge field, which lives on the link of this bond. And this dashed line corresponds to the magnetic flux in this plaquette, which comes from this third term here. So on the lattice, the curl of theta just means you sum the value of theta around a given plaquette, and this corresponds to the magnetic flux that's inserted in this lattice. So theta here just corresponds to an angular coordinate, and L is its canonical conjugate variable. And this J here describes the gauge fluctuations on the lattice. So what they observed is that for even numbers of n, where n is the number of flavors, there was no sign problem in the quantum Monte Carlo studies, and they observed that for small j, when this first term is roughly irrelevant, they do indeed observe a U1 spin liquid. So that was an exciting result. To, as I said, QED-3 is known to be a conformal field theory for large n, but here, even for small values of n, they do observe a U1 spin liquid phase, and they observed that at sufficiently large j, there's a transition to an appropriate magnetic phase, and these phase transitions were observed to be continuous. So they believe that there are no monopole operators which are important, and monopole operators are crucial in lattice QED, which I will hopefully get a chance to discuss later on. So this is some confirmation of their results. Here they plot the spin-spin correlation function as a function of distance for small j, and we observe on this log-log scale that it's a straight line, so we have algebraic correlations, and they observe the same phenomena for the dimer-dimer correlation function. So there's no magnetic ordering. You observe this algebraic correlation for either spin or dimer correlation functions. And this plot here shows the flux energy per plaquette as a function of the coupling constant. And this just shows that the amount of flux per J is always continuous. So if you were to have a discontinuous transition, or if monopole events may be important, then one might expect that at the critical value of J, that this flux energy undergoes some discontinuous behavior, but that's not observed. So it's believed that the transition is continuous. And in this paper, they conjectured that the description which would describe this transition from the U1 Nael to the U1 to the Nael phase would be the an O3 variant of the QED-GN theory that I mentioned earlier. And they also conjectured that the U1 to VBS would be described by a, that should be O2, QED-O2 GNY. And so what I'm going to just briefly present is that we can indeed show that this rotor model here does map onto these theories, and we can also calculate the scaling dimensions for these particular theories and show that they have some agreement with the Monte Carlo results.
Sorry, could I just, again, as a non-expert, just interpret? So you said dimer. What is a dimer in this setting?
So a dimer is something that illustrates the valence-bond-solid order. So for example, as I said at the start, you have this, at two different sites, you have this pairing between different spins on the site. So a dimer is like it's spin operator at a site times a spin operator at a site translated by one lattice spacing. So let's say the dimer operator D is like D of X is like S of X times S of X plus A. So it tells you I have a spin operator at site X, and then I look at the spin operator at site X plus A. That's how you would define the dimer operator in a dimer. Yes, go ahead.
So is that the same, or is it related to the idea of dimers in graph theory?
I'm not an expert on graph theory, so I wouldn't know the answer to that.
Well, you have to have bivalent graphs, and the black and white connected together forms a diamond. A dimer.
I don't know the answer to that. I'm sorry.
Okay.
In the interest of time, let me just move ahead a little bit. So we can show that the low energy theory for the particular rotor model is indeed described by the O2 QED-GN theory. So the important point here is that you have now a scalar field which has two components, and it's coupled with this M here as a vector, which has some matrix structure for each component. And what we find is that in the case where the scalar field has zero vacuum expectation value, this corresponds to the U1 quantum spin liquid phase. And when this scalar field gets a vacuum expectation value, that describes the valence-bond-solid phase. So this scalar field is tuning the transition between a phase with U1 symmetry and with broken O2 symmetry and unbroken O2 symmetry. One of the interesting things we found is that actually if you redefine the fermion fields and the gamma matrices in this theory, you can actually map it to the gauge Nambu-Jones-Lassigna model. And the utility of this is that in high energy theory, the gauged NJL model has been widely studied in large N. So all of the pertinent scaling dimensions for this condensed matter transition we're interested in have already, almost all of them have already been calculated in the high energy literature in the context of the NJL model. So I'll just move ahead and say that in the original quantum Monte Carlo paper, they obtained this U1 spin liquid phase, and they also looked at correlations in the antiferromagnetic valence-bond-solid phase, but they didn't they were not able at the time to calculate the scaling dimensions of those particular phases. However, more recently, Ziyang Meng and other collaborators have now calculated I've done more refined quantum Monte Carlo calculations. So this is a plot here of the scaling dimensions for the VBS phase. The curves with the error bars are their results. The dashed green curve corresponds to it's a particular type of, it's a scaling dimension of a particular operator that exhibits some staggered order. That's not too important for the moment, but the blue dashed curve is the scaling dimension for the VBS order parameter, which is the scalar order parameter that I just mentioned to you on the previous slide. And here they've done large n to 1 over n, and these results are roughly in reasonable agreement. But I will just mention that what we did around the same time as this paper came out, we did large n to 1 over n squared, and we found that the coefficient of the 1 over n squared term is actually positive, so that would pull this dashed curve up a little bit, which would make this agreement somewhat better. These brown and yellow lines correspond to the scaling dimensions for the ungauged O2 GNY theories. So they're just showing that it's not an ungauged theory. It's described by the gauged QED-3 O2 GNY theory. They haven't done the antiferromagnetic calculation yet, but we have the large N and the epsilon expansion results for the scaling dimensions of the pertinent operators in that transition. So that will be the next quantity to look at. So this shows, though, that the conjectured transition that they were observing in the quantum Monte Carlo is indeed described by this low energy theory. So in the interest of time, I will, I'll just skip the nail part and I'll move to this final summary. So what I have been discussing is how these QED-3 Gross Neveu Yukawa theories can describe different transitions. The QED-3 O3 GNY theory describes a transition from the U1 quantum spin liquid to a Nal phase. The QED-3 O2 GNY describes the transition from a quantum spin liquid to a valence-bond-solid phase. That's the one I just described. And earlier, as I mentioned, this Eisen case where you have a single scalar field describes a transition from a quantum spin liquid to a chiral spin liquid. And another transition, which I will possibly get to, is this, as was mentioned right at the start, this question about the Higgs analogy. This is a theory where we will see some similarities to that. But this pictorial representation of these transitions is very illustrative. It's quite amazing that you can start off with three-dimensional quantum electrodynamics, which describes this U1 spin liquid. You can add the O3 or Heisenberg GNY interactions that allows one to go to an ordered magnetic phase, describing the Nal phase. Then you have this deconfined quantum critical point, which allows one to go from the Nal phase to another magnetically ordered phase, the valence-bond-solid phase. This allows one to go back to QED-3 using the QED-3 O2 GNY theory. And that's also a theory which has a spin liquid transition to a chiral spin liquid. And it's conjectured that these critical points between the Nal VBS is due to the transition between the U1 spin liquid and the chiral spin liquid. So this picture here shows a lot of very rich structure in all these different phases. You have Nal and VBS, which are magnetically ordered phases. You have U1 quantum spin liquid phases and chiral spin liquid phases, and this other phase, which are not magnetically ordered phases. So the final topic I want to just briefly discuss, the notion of monopole scaling dimensions, which are very important when we're considering lattice calculations. This is recent work that was done here in collaboration with William. So let me just give you some brief summary of things that you already probably know from electromagnetism. So we know that Maxwell's equations, they do allow for a magnetic monopole, but as we conventionally write them down, they don't have a magnetic monopole. The divergence of B is 0. And if we write that the magnetic field is the curl of a vector potential, then it immediately follows that the divergence of B is 0. So if you want to have magnetic monopoles where the divergence of B is non-zero, then it must mean that your vector potential is singular, and that leads to what's known as the Dirac string. So one cannot have a magnetic monopole solution that has a vector potential which is well defined in all of space. So usually people put this Dirac string either on the northern hemisphere or the southern hemisphere, and you look at the region of space and opposite this region where you've put this Dirac singularity. I'll just mention that Ter Hooft and Polyakov had a very nice mathematical argument for how one can see if a theory has monopoles in it. They showed that if we consider the symmetry breaking of a symmetry group G down to some subgroup H, then there are monopoles in this theory if the second homotopy group of the coset G mod H is non-trivial. And using this, we can actually show that the standard model actually does not have magnetic monopoles. So if you go through the calculation, the real point is that the U1 hypercharge we have in the standard model, SU2 weak cross U1 hypercharge, leads to a non-compact U1. So this U1 electromagnetism, it's embedded irregularly in the SU2 cross U1. So it turns out that it's non-compact and it has no magnetic monopoles. But there are other grand unified theories like Georgi, Glashow, which do allow magnetic monopoles. But in the condensed matter context, magnetic monopoles are very natural. This is because the vector potential is not, it's not a continuous object, it's periodic. So the vector potential A can have, you can add up to 2 pi times an integer. And so this means we're allowed to insert magnetic flux in this particular lattice. So these flux insertion operators are what we mean by a monopole operator. And we want to determine whether or not these will destroy this U1 spin liquid phase. I'm just going to be quite quick to get to the main punchline, but Polyakov showed that in a pure U1 gauge theory, these monopole operators proliferate and they actually can confine the gauge field. And what happens is if you have a large number of massless fermions, these actually screen the monopoles. So this is a monopole-monopole correlation function. And as you can see, if we have enough massless matter, we can actually screen this proliferation effect and have a stable gapless phase. And this is important because what I've been talking about is the transitions from the U1 phase, and I haven't really mentioned monopole operators. So we want to make sure that the U1 quantum spin liquid phase is indeed stable. So it's important to know, do these monopole scaling dimensions really affect the transition? That is, do monopole operators proliferate or not? So should I, just a question, William, should I be very, how much time do I have? A couple minutes?
Like 3 minutes, something like that, 3-5 minutes, not more.
Okay, I'll just say that we want to calculate monopole scaling dimensions because they tell us whether or not the U1 spin liquid is stable or not. So if monopole scaling dimensions are large, we can ignore the contribution to them. And if they're very small, then that means that monopole scaling dimensions can be important. So what we have done is recently we have calculated monopole scaling dimensions to subleading order in the large N expansion. So N here is the number of fermion flavors, and this is the subleading correction. This calculation was done in the context of three-dimensional quantum electrodynamics, originally by Pufu and his collaborators, and these are their results. And here we have redone this calculation with some slightly improved precision, but nevertheless we find that for the case of QED3, we do have the numbers are very, very similar to one another. And I just want to mention that this monopole scaling dimension for the lowest order monopole is actually part of this duality web that I mentioned earlier. And the value that we get for the lowest charge monopole when n is 2, it agrees with all of the various numbers that have been calculated in the literature. And finally, I'll just mention that one thing we've also done to check our monopole calculation, so to speak, is it's quite interesting that in a theory that has a global U1 symmetry, the operator that's charged under this U1 symmetry has the following large charge expansion, and this parameter gamma here is a universal constant. And you can show that it has a numerical value given by this number here, which is universal. It has many other digits. And using our monopole scaling dimensions, we've calculated this parameter gamma here using the large charge expansion, and we found that to within order numerical error, we roughly reproduce this value. So let me just very briefly summarize and say that I looked at this duality conjecture for the spin liquid transition and the Mayal BBS transition, and the scaling dimensions were roughly in agreement with that. I also showed that the scaling dimensions for the order parameter in the U1 spin liquid to BBS transition agreed with the quantum Monte Carlo results. And here I've also briefly mentioned some of our monopole scaling dimension calculations, and we've seen good agreement with some expectations for this universal coefficient, which comes from conformal field theory. And we also found compatibility with this duality. So thank you very much for your attention.
Thank you, Rufus. So we have some time for questions, so that's good. So I'm going to open a talk to more questions. We already had a few questions, but if people want to add more,
so
please feel free.
I have a couple of questions. One is it's not completely clear to me at the end. These monopole operators in these dualities that you have, are they dual to other monopole operators, or are they dual to some other types of operators?
Right, yes. So they are dual to other types of monopole operators. So there is a monopole, I'll just go back. There is, here we've calculated the monopole in QED-GN, and it's conjectured that this monopole operator should be dual to the Cp Cpn-1, where n is 2, so Cp1 monopole. And the large N calculation for that has been done by Pufu and Sachdev. So these are different monopole operators. So they're completely different calculations. This monopole is for this fermionic QED-GN theory. This monopole operator is for this bosonic theory.
Yeah, but it's still monopole always corresponds to a monopole in the other theory.
Yes, correct.
That was okay. And the other question is
maybe just words if I intervene a bit. It's a good question. I mean, if the SO5 duality is correct, then you have SO5 multiplets that are dual, and so yes, the monopole on each side belongs to the dual multiplet, but there are other operators, right? So on the bosonic side, there are other operators that are not monopole operaters.
Yeah.
And I think Rufus is even showing some
yes
results, right? So Rufus, I mean, the 0.3, that's not a monopole, that's bilinear of the bosonic field Z dagger sigma Z.
That's quite right. That's quite right. All components of these order parameters are equal. So this is not a monopole operator. So yes, apologies, I was a bit glib, but the monopoles are dual to other monopoles, but they're also dual to other non-monopole objects. So it's a much stronger constraint than that.
I got a bit lost keeping track of all these. When you say large NCP1, do you mean
And there's the number of.
It's a gauged linear sigma model or a non-linear sigma model, or.
And there is the number of scalar fields. So
yes.
it is it's a model with just scalar degrees of freedom, just complex bosons.
Yes, but
it is a sigma model. It is a nonlinear sigma model with.
It's a nonlinear sigma model. Okay, so there's no gauge field there.
No, there is. It's a gauged nonlinear sigma model.
It's
so
a
take
gauged
your
nonlinear
regular
sigma
model and then gauge the U1. There's a U1, diagonal U1, and gauge it.
That's right. It's gauged Cp1. Yeah.
Okay. And the other question that I had was, so if you take these, these fixed points that you have, and then you start adding a Chern-Simons term, that will gap the vectors.
Yes.
So would this correspond to something physically interesting for these models? Of course, it's not a continuous deformation because it's not like it's a Chern-Simons term.
We wouldn't consider the Chern-Simons in the case of the QED-GN because there we want to spontaneously break time reversal symmetry, but the Chern-Simons term would explicitly break it. So we wouldn't consider it in that case. You do find that you get a Chern-Simons term in the infrared in the QED-GN transition, which is as a result of the fermions acquiring a mass. So that's, you could say one is emergent, but we wouldn't put one in by hand, no.
Okay. Thank you.
Just a naive question. I mean, there are presumably in the lab observable quantum spin liquids, aren't there?
Well, the U1 quantum spin liquid is the one that's of interest here, and that is the thing is that it's defined via it's defined by what it's not. It's defined to be a system which does not have paramagnetic order. So it's actually not easy to say definitively that you have a spin liquid. The ones that I mentioned right at the start are the most famous ones. So if you look in the literature, people often say that Herbert smithite is believed to be a quantum spin liquid, and this organic material is believed to be one. There are many types of spin liquids, gapless, or it's a very rich field, but coming up with a definitive test of what it is not. If you look at people who try to define what it is, they use various things like heat capacity to check for gapless excitations. Even trying to look at, say, the magnetic susceptibility is something that's done using magnetic resonance, but there's no, you can't 100% say you have something. You can just say that you've observed features that are similar with it. So yes, I'm just saying that the spin liquid here, the U1 spin liquid, is not, it doesn't have a positive formulation, so to speak. It's defined somewhat in a negative sense, that it has no magnetic order. So when you want to say you don't have...
I'm just bewildered. I mean, is there a material which is known, which can be seen in the lab, which is a quantum spin liquid?
Well, not that everyone agrees upon. The short answer is no.
Okay, so my obvious question was if the critical phenomena can be observed, but if you don't even know if you have a quantum spin liquid, I guess it's not worthwhile asking the question.
Yes.
Or maybe that could be a part of the answer to the question.
That in the mathematical physics seminar.
Yeah, well, we'd like to be rooted in the real world.
That's right. No, but I mean, we have models that are realistic, like the Heisenberg model on Kagome lattice, which is like the simplest model you can write down on that lattice, and that there's evidence that this Dirac quantum spin liquid as its ground state. And then, as a theorist, the perspective sometimes is that, well, experimentalists need to do a better job and find a better material that's cleaner, and it will have these phenomena. But in terms of can it exist? The answer is definitely, well, okay, it's not that simple because maybe it's not exactly stable. Depends on the number of Dirac flavors, but if you have enough Dirac flavors, the answer is yes. And I think numerically and from field theory and from bootstrap, and so it's like a hunt, that's what it is. And in terms of field theories, these are beautiful field theories with a lot of properties. This web of duality between different conformal field theories is one example. So people from different fields are interested in such transitions, and here they happen to describe some conjectured phase transitions. But even getting a spin liquid, the simplest ones, Dirac is not the simplest one. There are simpler ones. It's quite challenging in the lab. But it's I think people haven't given up.
So this thing, which is zinc, copper, etc., the picture on the slide on the left, that's presumably not a quantum spin liquid. But what is that?
That's Herbert-Smithite. It's believed to be a quantum spin liquid.
But can one do experiments? I mean, first of all, I'm not sure what the parameters are, but how will you go about looking for critical phenomena in such a thing?
Well, this plot here with these green and blue things is an experiment on Herbert-Smithite. It's neutron scattering. Neutron scattering experiments, you flip an electron spin and you get a resonance, right? You excite if you have a system that has magnetic order, there'll be a peak in your spectrum. So you'll see that you excite a magnet, which is a collective excitation in the magnetic system. But here, this is the energy of the neutron system. So it goes from 0, let's look at the right-hand one, let's say, goes from 0 to 12. So if I look at a fixed wave vector in the system and I apply neutron scattering for all range of energies, there's no peaks, there's no resonances. So this clearly is a system that does not have magnons in it. So there's no, well, not clearly, this is very suggestive that this is a system that has no magnon excitations. So it has no magnetic ordering. If it has no magnetic ordering, that's the first thing we would require for it to be a spin liquid. So this is proof that's very compelling that it is a spin liquid.
So if you actually wanted to do some kind of critical point experiment, what would be the parameters that you control?
To test if it's a spin liquid, or to test if it's
drive a phase transition.
There's a critical, but the phase transition.
Oh, on an actual material?
Yeah.
That's a good question. Well, you would find out what the parameter that tunes the transition is, and if you know how it behaves on either side, then you would know whether or not it's a good candidate for the transition between the two phases. So I would have to think more about. I can't give you a good answer off the top of my head as to that at the moment.
Maybe I could just say a little anecdote, which this reminds me of. You say whether it really exists or not. I once, a long time ago, went to a lecture given by Juan Maldacena, and he was talking about the ADS-CFT and how wonderful this sort of maximally extended super Yang-Mills was, and so on. And I asked a question which was pretty naive. I just said, well, are you at all bothered by the fact that there's no evidence of either supersymmetry or conformal invariance in the real world? I mean, conformal invariance in the real high energy world. And he just he just sort of looked puzzled and frozen for a moment. It didn't say anything. And then it was like a light bulb came on. And he said, "Oh, you mean in the real world?"
Well, I would say that this is not quite as that. We have quantum Monte Carlo. The quantum Monte Carlo simulations have simulated this transition. We also can do transitions between Néel and BBS phases. We know explicitly what those magnetically ordered phases are. We know very well what the order parameters are for Néel and BBS. So if we have materials that have properties which do have signatures of quantum spin liquids, as I've illustrated here. So I don't think it's totally, what we are discussing here is totally as theory motivated as not to, you know, not a string theorist myself, but I'm just saying that what we are working with are tools that are very realistic, realizable in laboratories. So I think we do have a handle on the constituents that we are dealing with. It's okay, we don't have a quantum spin liquid in the same way that we have a metal that is a superconductor, say aluminium, or a high TC superconductor, YBCO, these sort of things. But we have the candidates, and we have the tools that can give signatures of that. So I would say that we still are in the realms of the real world at the moment.
Well, as a long time separated from the world of theoretical high energy physics, but that's where I started out. But condensed matter, especially this rather sophisticated condensed matter, is, well, the nice thing about it is that one hopes to be able to actually take the theoretical predictions and be able to bring them right down to observation.
Absolutely, as with all of physics, I would say.
On this note, this this is a very important note about physics. I think we've asked enough questions of Rufus. So let's thank again the speaker for a nice talk and answering a lot of questions. And we'll see you next week at the same time, or perhaps even in person if you wish to attend the talk by Benjamin Doyon.